Okay, we are working on section 3.1, and this is going to work with max and mins. We're going to look at local and relative mins, or we will also look at absolute and global min and max values. We'll talk about the difference between being on an open interval versus a closed interval, and why might we want to find the max and mins of functions? Well, it allows us to optimize situations, and in many cases we want to find where we can make the most money or where we can grow the best crops. All these real world problems where we might want to find the maximum or the minimum of a scenario, like the minimum costs in a manufacturing situation. So I have this function f of x equals x squared divided by the quantity x squared plus 4, and let's find the derivative. Well, that would be making use of the quotient rule, wouldn't it? So I'm just going to go ahead and reveal here is the derivative once it is completed. What I noticed with this function and its graph is there is a minimum value. This would be a local minimum right here, and it occurs at 0, 0. Well, what is true when we hit a min is that the tangent line would have a first derivative that's equal to 0 at that location. And so if I take this function, this function's derivative, set it equal to 0, I could see, well, to get this equal 0, 8x would have to equal 0, which would imply that x is 0. And wouldn't you believe it? Right there it is. The min is occurring at an x value where x was 0. On this next problem, number 4, we have the cosine of pi times x divided by 2. And if we took its derivative, we'd have to use the chain rule. And the derivative of cosine would give us negative sine of pi x divided by 2. And then I would multiply by the inside derivative, which would give us pi over 2. And so we could write this function as negative pi over 2 sine of pi x divided by 2. Well, looking at this function of cosine, I hit a max and a min in this short span of what we're seeing for kind of a close-up view of the function. And we would be able to say that the derivative is equal to 0 would give us some tangent lines that have horizontal tangent lines. These points would be in line with that. And so if I took my function negative pi over 2 sine of pi x over 2 and set it equal to 0, I should be able to find the locations where this would occur. So I've got this, I could divide by that and it will go away. So then I'm left with sine equals pi x over 2. Well, where does sine equals 0? Well, sine equals 0 either over here on the unit circle or over on the left side we're equal to 0 as well for sine. So I would take 0 and set it equal to pi x divided by 2. And I also could take negative pi and set it equal to pi x over 2. And in this scenario, if I multiply by 2 and divide by pi, I get x equals 0. So no surprise that at x equals 0, we're seeing a max or a min. And on this other scenario, part B here, my other option, if I multiplied by 2, I'd have negative pi equals pi x. Divide by pi, and x equals, should be positive 2, shouldn't it? Yep, because I'm dividing by negative pi. So x equals positive 2, and we get the two locations there. So the definition of a local maximum, also sometimes you'll see it referred to as a relative maximum. The AP will use both terminologies, so be familiar with them. It says f of x is a local maximum value of f if f of c is greater than f of x for every x in some interval. This I is standing for an interval, and that interval could be defined however. So So if I look down here, I can see what my interval is being defined as. So in this interval, do we have a local maximum? Well, yes, we do right here, because this y value is greater than all other y values in this interval. Okay, so there's a particular y value. This f of c is greater than all the other y values in this particular region. So it's a local one. We're locking in a certain range. It is the highest point in that local area. On the screen to the right here, there are two locations where I see a local maximum. One would be here and right here. So this would be A and B would be our local maximum. I could not discuss this one because I don't know information to the right of it. You know, maybe it continues to go up, maybe it doesn't. So we can only discuss about a local interval. Definition of local min, also referred to as a relative min. The definition is sort of similar to what we talked about with max. F of c is the local min value if our y value we're selecting is less than or equal to all y values in a local area in some local interval I. And so here we see that this produced the lowest spot of all y values in the local region. So it's a local min. Over here on the screen on the right, I pick up two local mins. I'll just call them C and D, because in the region surrounding them, they are the lowest y values. We pick up a theorem, and the theorem says if a function has a local extremum at a number c in the open interval, then either f prime of c is equal to 0 or f prime of c doesn't exist. This is a really powerful statement here, and it's talking about how to find local extremum using calculus. And you notice we're talking first derivative here. So if the first derivative equals 0, or if the first derivative doesn't exist, we have suspicions that a local extremum exists there. So a local max may occur at a point where the function is not differentiable. We know that sharp points occur when we get a not differentiable function, but that doesn't mean that we can't have a maximum. There's still points that exist there. It's just that the derivative didn't exist. And it could be because it reached a sharp point. Over here, I pick up that tangent line that has a horizontal slope to it. The slope was 0. So that's the case where f prime is equal to 0. Often we talk about critical numbers, and the critical number c in the domain of f, so it does have to belong to the domain of f, is a critical number of f if either the first derivative is equal to 0 or it doesn't exist. So these values here that we're picking up where x was equal to c, we're going to call those critical values. And either it's from the first derivative equaling 0 or not existing. So example 1, find the relative minima or maxima, which are the plural words for minimum and maximum, over the region shown. So I would say relative min or max. We have a relative max here, correct? We have a relative min here. I have a relative max, and I have a relative min at f. At all these locations, I would discover that f prime of x was either equal to 0 or it didn't exist. This one here is not a relative min, because in the local area, I can't tell you if it's the least value. Okay. Relative mins and maxes do not occur on endpoints. Over here on the right, you see the picture shown. Find all the critical values of h on the interval, and then determine if it is a local max. Well, the critical values are going to come when h prime of x is equal to 0 or is not existing. It doesn't exist. And I would say that I would have problems at x equals -1. Ooh, I missed one. At x equals -3, I would have issues because the derivative wouldn't exist. We have discontinuity, right? And if it's not continuous, it's not differentiable. At x equals -1, once again, we have jump discontinuity. If it's not continuous, then it's not differentiable. At 1 would be another critical point because it's not differentiable. At x equals 2, it's not differentiable, so I pick up that option as well. And the endpoints can never be relative mins and maxes, so they are not critical points either. We could describe at -3, this point here would be a relative max because in the local area it is the highest point. We have a relative max for all values in the range from what, -1 to 1, relative max for C values sitting between -1 and 1, excluding our endpoints. And I pick up a, nothing happening here, is it? Because this particular point is lower than the one surrounding it. So neither a max or a min here. And endpoints, we're going to exclude endpoints from the discussion of relative mins and maxes. So on the back here, find all critical numbers of the function f of x equals 8x cubed minus t squared. And the domain, let's discuss the domain. Well, I noticed the first thing is that f of x is a polynomial. And if it's a polynomial, that implies right away that it is continuous everywhere. And so our domain will be -infinity to infinity. The first derivative, let's take the first derivative. It'll be the first step in finding critical values. So I get 24t squared minus 2t. And I want to find critical numbers. These are possible mins and maxes. All right, so if I take my derivative and set it equal to 0, I'm going to take 0 equals 24t squared minus 2t. How can I find values of t that give me 0? Well, the easiest way, I think, will be to GCF first. So let's pull a 2t. That'll give us 12t minus 1. And then let's set each of these factors equal to 0 and discover our critical points. So at t equals 0, we have a critical point, and at t equals 1/12, we also have critical numbers. So critical numbers are those two. Do we have any spots where the first derivative does not exist? Well, remember that first derivative was 24t squared. This is a function, and the first thing I notice about it is a polynomial as well. So this polynomial exists everywhere, and I wouldn't have any sharp points. It's continuous. It's differentiable everywhere. It exists from -infinity to infinity. No sharp points. It's differentiable everywhere. So we would have no critical values or no critical numbers coming from D and E. Just keep in mind critical points also have to fit in our domain. So we ended up with those two critical numbers. All right, we hit a bunch of words here. The definition of an absolute or global extrema value. If f is a function on an interval I, then y equals f of c is the absolute maximum on that interval I if and only if f of c is greater than f of x for all x's in the interval. And then we could talk about it being the absolute. The absolute minimum says that our particular y value is less than all other y values for all x's in the interval. If f is continuous on a closed interval, then f has both a maximum value and a minimum value on that closed interval. Notice, this is called the extreme value theorem. Oh, I missed that. The extreme value theorem guarantees the min and max. It guarantees it, but it doesn't tell us exactly how to find them. But we do know they exist, so that's kind of cool. And the theorem, the absolute extrema can occur only at a critical value or an endpoint. Oh my gosh, that's pretty powerful. It's telling us that these absolute mins and maxes will either be at a critical value, which we can get when we take f prime of x and set it equal to 0, or find where it doesn't exist. The other spot that they can exist is at endpoints. So we have to, be sure and look for our endpoints too and test out, because they might be the absolute. So just a little bit of steps here about how to find your absolute or your global extrema on a continuous function that is that's on a closed interval. First, identify your endpoints. You don't want to forget to check out endpoints. Also, next, identify any critical numbers of f in the open interval a to b, and verify that they are in the domain of the interval. Third thing, find the function's value, which f of x, this is really meaning a y value, at both the endpoints and all the critical values that we came up with in step number 2. We're going to find their y values, and then we can compare y values to see which one has the biggest. The greatest value, or the greatest y value, will be the max, and the least y value will be the min. So let's give it a shot. Example 3, determine if the EVT, which stands for extreme value theorem, applies. If so, find the extrema for the function on the given interval. Notice it's a closed interval, -1, 2, 3. Well, does the EVT apply? Two things that has to happen, and we have to have a continuous function, and it has to be on a closed interval in order to guarantee that extreme values do exist. Okay, so we do have that, don't we? We have a closed interval because we can use 0, we can use negative numbers. Our domain for this function is really going to be -∞ to infinity. And so obviously it is existing on the interval from -1 to 3. Endpoints. Let's identify our endpoints. Well, our endpoints are x equals -1 or 3. The first derivative, let's take our first derivative. It will be 2 minus 3 times 2/3 x to the 2/3 minus 3/3, or -1. And that gives us, let's kind of clean this up, minus 2x to the -1/3. And we may want to just write that as 2 minus 2 over the cube root of x. So there's our first derivative. From that, we can find our critical numbers. Well, can I ever get this equal to 0? Perhaps we can. Let's set it up. 0 is equal to 2 minus 2 over the cube root of x. And to solve that, we would let's add 2 over and set it equal to 2. Then I'm adding it to the other side. Multiply up by a cube root of x. Divide by 2, and I have 1 equals the cube root of x. Cube both sides, 1 is equal to x. So I end up with a critical value at 1. Does it not exist anywhere? Yes, that could happen, couldn't it? If I used 0. I'm looking, where would this function, where does the derivative function not exist? When the denominator equals 0. Would be problems, right? For its domain there. And I would just check this out. Well, the denominator can't equal 0. That would imply if I cube both sides that x would equal 0. So I come up with these candidates for my max, absolute max, and absolute min. So I get the candidates. I need to check out my left endpoint. I have a critical point at 0. I have a critical point at 1. And I also need to check out the right endpoint at 3. So I ended up with 4 candidates. Take and insert insert -1 into the original function. F of -1 would look like 2 times -1 minus 3, -1 to the 2/3 power. If you do that work, you're going to get -5. If you put in 0 to our original function, you will get out 0. If you put in 1, you're going to find it to be -1. If you put in 3, you're going to get 6 minus 3 cube root of 9. Judging all of these values, and this you might want to use a calculator to come up with that, I can see that the least value is f of -1. This would be the absolute min. And the absolute max is going to be right here at 0. The absolute max occurs here. So it has an absolute min of -5 and an absolute max of 0. It occurs at x equals -1, and the absolute max occurs at x equals 0. When they ask a question, or when you're asked about what is the absolute min, it's looking for the y value, or the absolute max, it's looking for a y value. If it asks where it occurs, then we're talking at the location x equals. That's probably enough for this particular video, and I'll continue on part 2.